Good morning, dear students. So far we have discussed D block element completely. Today we are going to see the new chapter of the chemistry, coordination chemistry. Coordination chemistry. What is coordination chemistry? As we studied in the previous lessons, the D block or transition elements have a tendency to form a compound complexes. Okay. Comparatively, other non-metal, only the transition metals have the lot of tendency to form a complex that we have learned earlier. Now, the compound formed have a different property comparatively to the ionic and covalent compounds. For example, if you take a chromium 3-chloride and hexahydrate, chromium 3-chloride and hexahydrate, if we take, it is existing in 3 different colors. Okay, purple and pale green and dark green. So these are the different forms of the same compound complex. So we are in the position to learn what is the coordination compound, what are the properties of coordination compound, and ligands and central metal atom, isomerism and applications, everything we need to know. In our day-to-day life, blood, it is a coordination compound of Fe2 plus because hemoglobin is there, no? Fe2 plus hemoglobin. This is a coordination complex of Fe2 plus. For a plant, if you take a chlorophyll, this is the coordination compound of Mg2 plus. Okay. So for animal blood, if you take a hemoglobin and a chlorophyll, for a plant, if you take a chlorophyll, that is a Mg2 plus, all are a coordination compound only. And then in addition to the industrial purpose, Wilkinson catalyst, and Ziegler-Meta. These are the industrial catalysts which is used in the industries. These all are come under the coordination compounds only. So we need to learn about the coordination compound. What is the coordination compound? What are the component terms and terminologies and their properties, structures, isomerism and uses that we are going to see now. Okay. Before entering into the coordination compound, we are going to know about the different type of salts. Normal salt or simple salt. So NaCl, for example, NaCl, if you take a cation and ion come mixed together to form a simple salt. Okay, that is NaCl. An acid and base react to give a simple salt. Okay, for example, NaCl. This NaCl can dissociate it into Na plus and Cl minus into constituent ion. This is simple salt. Then we have a addition compound. Addition compounds. There are 2 types of additional compounds. First, before that, what is the additional compound? Additional compound or addition compounds are nothing but a 2 or more simple salts combined to give an additional salt. 2 or more simple salts combined to give an additional salt. Okay. For example, if you take a FeCl2, it is a simple salt, plus 4KCl, it is a simple salt. These two combine to give a K4FeCl6. This is a complex. Okay. Still more example you can have. Then the addition compound can be classified into two types. Additional compound can be classified into two types. Okay, two types. One is a double salt. Double salt. Another one is a complex, coordination compound. Coordination complex. Complex or compound, double salt. The complex, coordination complex is the word, Latin word. It's a meaning, coordination compound meaning. This is nothing but a hold to arrange. Hold and to arrange. Coordination complex. Okay. What is double salt, sir? Here, two simple salts are combined together to give a double salt. For example, FeSO4 plus ammonium sulfate against for twice SO4, 6 times of H2. Ferrous sulfate and FeSO4 to combine to give a more salt. This is called more salt. More salt. So FeSO4 dot NH4 twice SO4 and 6H2. This is a double salt. Okay, what is the specialty in double salt? Double salt also can dissociate simply into, like a simple salt. If we dissociate it, you are getting that Fe2 plus ion plus SO4 2 minus ion plus NH3 plus ion. These are the ions. The constituent ions will coming out from the double salt. Okay, when a equimolar solution of two simple salt combined to give a double salt, the double salt will dissociate easily and give a constituent ions. The double salt loses their identity. Okay. Now let us move on to the coordination compound. For example, if we take this is the same example you can write. This is a ferrous cyanide, potassium cyanide, two simple salt combined to give a the complex formation, potassium ferricyanide. This is a complex formed between these potassium ferricyanide. So this is a, now if you are dissociated into, it will not dissociate and to give a constituent ions. Instead of this, it will give a cation and a complex anion plus FeCH6 4 rings. So you cannot get individual ions like K plus Fe2 plus Cl minus you are not getting. So they do not dissociate it to give a constituent ion. This is a major difference between the double salt and a coordination compound. Double salt, it's also a combination of two simple salt. This also a combination of two simple salt. But what is the difference here is it is ionized and dissociated to give a individual constituent of that salt. But whereas it will not give a individual constituent of that salt. That is called a coordination compound. So here something is there. The extraordinary bond is there, or a different type of bond present in it. That's why they are not dissociated to give a constituent ion. What is the bond? We know that ionic bond, covalent bond, covalent bond. In addition to that, coordinate bond. Coordinate bond is there. What is called coordinate bond? You know, ionic bond is a electrostatic force of attraction between the positive ion and negative ion. This is called ionic bond. Okay, electrostatic force of attraction between the positive and the negative. Then a covalent bond is mutual sharing of atom. For example, methane, if you take mutual sharing of electron between the two atoms. How is mutual sharing? For this bond to be formed, mutual sharing. Hydrogen is contributing one electron, whereas carbon also is contributing one electron. Thus the mutual sharing between these two. That's why the covalent bond is arised. This is mutual sharing, the electrostatic force of attraction. Now what about the coordinate bond? Coordinate bond is nothing but it's a type of covalent bond, but there is one donor and one acceptor. Maybe the donor donating and acceptor. Donor is donating, the acceptor. So that the symbol is given like this. Okay. It is also covalent bond. To differentiate the covalent bond and coordinate bond, we are representing the covalent bond into this diagram. Coordinate. Where is donating? From this side to that side. This substance donating the electron towards that substance. The total entire bond formed only the contribution of one side. This side only contributing the bond formation. Whereas in a covalent bond, if you see, for this bond formation, you need a cooperation, the mutual sharing of electron between the carbon and hydrogen. But it is not so in the case of here. Here only one atom is donating or contributing to the others. One is donor, one is acceptor. That type of bond is called a coordinate bond. That coordinate bond exists in this coordination complexes. Okay. Now let me list out the difference between the double salt and the coordination complexes. Okay. Now let us see the difference between double salt and the coordination complex. It is exist only in a solid form. It is exist only in a solid form. Whereas it exists both solid and aqueous. In aqueous form also it exists. There is no coordinate bond. No coordinate bond. But here coordinate bond is there. Coordinate bond is there. Then dissociates into ions, constituent ions. Does not dissociate into ions. Constituent ions, not simply ion, constituent ions. Constituent ions mean the ions which contain this. Then lose the identity. Do not lose the or does not lose the identity. What do you mean, sir? Lose the identity mean if you double salt is taken, when you more salt is taken, for example, the FeSO4, its crystalline form it exists double salt. When you put into the solution, okay, then it will give a constituent ions only. It will result for all constituent ions Fe2 plus dissociate into Fe2 plus, SO4 2 minus, and NH4 plus. Like this it will be dissociated. So if you do the test for Fe2 plus, it will answer. If you do the test for SO4 2 minus, it will be answer. It will be do the test for NH4 plus, also it will be answer. But where is the identity of the more salt? More salt has some, in a crystalline form, it has some different property, individual properties there. It loses their individual property, but it will behave as the ions in a solution. It will behave as the ion in a solution. You cannot have the property of double salt while mixed in the solution. That's why it exists only as a solid. We are saying there is no coordinate bond and it dissociated into constituent ions and loses their identity. Okay. In opposite to that, the coordination complex, if you take, it can exist in a solid and aqueous form. For example, K4FeCl6. Okay, if you take the coordination compound, it's an additional compound. It is also made by 2 salted. But what is the problem? If in solid also it will exist the same. In aqueous solution also it will behave as the same. If we dissociated, if you ionize, it will give a only 4K plus FeCN6. Like a complex ion will be formed here. The complex ion will not behave as a, you cannot expect K plus Fe2 plus Cl minus, you cannot expect. This will not be formed. Only K plus and complex ion is formed. That's why it does not dissociate into the constituent ions and do not lose their identity. No, it will behave in the solution also. Then one more point we can take. Always double salt, the two salts should be equimolar. Equimolar solution should be taken. Equimolar solution should be taken. Then only you may be, the double salt will be formed properly. But here, may or may not the equimolar solution. May or may not equimolar solution. If you take a definite amount, equimolar solution of ferrous sulfate and ammonium sulfate only, you can get a more salt, double salt. Whereas this is not necessary in the case of to get a coordination complexes. These are the difference between the double salt and coordination complexes. Let us deal with the Werner theory. Werner theory. So Werner is a father of coordination chemistry. Why he called as a father of coordination chemistry? He is the one who proposed first about the coordination compound. So he is called as a father of coordination chemistry. He assumed that how the coordination compounds are formed. By his postulates we can understand. For example, if we take with one example for a cobalt 3 chloride treated with ammonia. Cobalt 3 chloride treated with ammonia. It gives various type of products. Look. So this is the same but a different color is there. So he took this compound for the analysis purpose. Why the different colors arises? After the lot of experiment, he gives his postulates. What is there in this compound? The first postulates are the Werner's is first one. 2 valency. Each element having the 2 valency. What are the 2 valency? These elements. One is a primary valency. Another one is a secondary valency. Okay, primary valency and secondary valency. So let us see one by one. Primary valency. What is the primary valency? Primary valency related with the oxidation state. Oxidation state. Whereas secondary valency related to the coordination number. The definition of the oxidation state and coordination number we will see in the next class detailedly. Just I am saying here, if you take this compound CO3 plus, that is 3 plus is a oxidation state of this compound. The number of ligands mixed together. If you take this one COCl3 6NH3, the 6 is a secondary valency coordination number. That is a secondary valency. 3 plus is a primary valency of this compound. Okay. And then the primary valency always satisfied by the negative ions. The primary valency always tend to be positive, in some cases 0. Primary valency always be positive, tend to be positive. That is oxidation state. Oxidation state of the central metal atom. Here central metal atom is cobalt. Okay, there is a primary valency 3 plus oxidation state. In all cases, mostly positive oxidation state only there. So primary valency always be positive, and in some cases, for example, iron pentacarbonate. Here you may find that the oxidation state of Fe is 0. Few cases the primary valency may be 0, but always it is positive. It is satisfied by the negative ions. It is satisfied by the negative ions. Primary valency being positive or 0, it is satisfied only by the negative ions. Okay, they are non-directional. They are non-directional. Primary valency satisfied by the negative ions. They are non. What do you mean by non-directional? There is no proper attachment with the central atom. That is called a non-directional. So there is no definite geometry for this. Okay, there is non-geometry. Then let us move on to secondary valency. Secondary valency is nothing but it is a coordination number, we said already. Coordination number, what do you mean by coordination number? Coordination number of atoms surrounded to the central metal atom. If you surrounded by 6, this is called a coordination number 6. How many atoms are surrounding that central metal atom? The exact definition for the coordination number, if you say, the chemical bond formed between the ligand and the central metal atom. So there are 6 for this complex. Coordination number is 6. Okay. So coordination number 6, it is always satisfied by the neutral molecule or negative or positive ions, sometimes positive ions. So all can satisfy this secondary valency, but the primary valency only satisfied by the negative ions, whereas secondary valency can satisfy neutral, negative, positive ions. Okay, this can be satisfied. It is a directional. This is a directional one. Primary valency non-directional, whereas the secondary valency is a directional one. These are terms he used, Werner. By comparing this, he is assuming this some concept. That is a Werner's theory that we are going to see now. So, if the metal atom having 2 spheres, central metal atom having 2 spheres, this is central metal atom. Around this one sphere is there. And another one sphere. So this is called inner sphere. Inner sphere, or otherwise coordination sphere. Coordination sphere. This will be outer sphere. Outer sphere, or otherwise ionization sphere. So Werner assumes that the central metal atom around this one sphere is there, that is called a inner sphere or coordination sphere. The outer sphere, the second sphere is called outer sphere or ionization sphere. Here ionization can easily take place. Okay. Now for this compound, 6 ammonia molecules are there. 1, 2, 3, 4, 5, all those 6. All all those 6 in the given as solid lines because the strong bond between the metal atom and the ligand, neutral molecule. Then, in outer sphere, if you take, these are our inner sphere area, okay. If you extend the inner sphere, because I have written ammonia like this is called inner sphere. Now let us have some gap for the outer sphere, because if you write ammonia inside, then you can. The inner sphere occupied by the neutral molecule ammonia. Then for the outer sphere, this is the outer sphere. If you take here, Cl occupying the Cl. The primary valence is occupying the outer sphere. Cl. This is non-directional, you can write anywhere else. See, on the direction character I have written in the solid lines. Ammonia to metal, solid lines I have drawn. Whereas non-directional Cl, primary valence is broken line. Again, once again, we can draw without confusion. Metal. In inner sphere, there is inner sphere, you have ammonia, neutral molecule. All are directional, so then outer sphere, they are non-directional primary valence, negative valence. There is no restriction for the negative valence here, like this. So the inner cell, that is coordination sphere, give you a directional. If a coordination number 6, then it is octahedral. Then coordination number 4, this is a 2 chances, tetrahedral or square triangle. Okay, these are the definite geometry is there. That is why they are directional. They represent in a solid line. Now this is a Werner assumption to give a formation of coordination compound. Okay. Once again, so after finding this, we may write this. What is a cobalt inside? Okay. Then inner cell satisfied with the secondary valency. Secondary valency satisfied with the neutral pieces. 6. This is the inner sphere outline. Sphere. 3 inner outer sphere. Okay. This is a coordination compound. This is coordination sphere, central atom, secondary valence satisfied with the ammonia, primary valence is there. Okay. So by using this assumption, let us discuss again the first compound, all those color variation and how they are being, how many moles are there to react. Like this we can see. So cobalt, NH3, 6 times Cl3. This is the first piece we have, right? Here 3 ionizable pieces, so it will give a 3 moles of AgCl. Number of moles of AgCl given 3. Because 3 Cl3 will be ionized easily, so you will get 3. Then CO, NH3, 5 times 1Cl and Cl2. Here, if you see the ionizable valence will be 2, it will give us 2 moles of AgCl. Then NH3, 4 times Cl2. You are getting Cl. Here only one ionizable pieces, you will get a 1 moles. What is the 1 mole AgCl? Here, if you put a Ag plus ion mixed to the Ag plus ion, how many replaceable Cl is there? That much of AgCl will be formed. Here 3 Cl ions can be replaceable, that is ionized. If you ionize this piece, you may get a CO NH3 6 times 3 plus 3 Cl minus. These 3 Cl minus treated with the Ag plus, you are getting a 3 AgCl. As a result, 3 moles of AgCl is formed. Whereas here if you see the same compound only, same, the component is not varied. Cobalt, ammonia, but how many Cls are outside? If you see if you go and see, only 2 Cl can be ionized. If you ionize this one, you will get a 2 Cl minus. So 2 moles of AgCl will be formed. If you ionize, only 1 Cl minus will be ionized. So you are getting only 1 moles. That's why the color variation, number of ionizable pieces varies. That's why the color also varying for this compound. Now what is the primary valency? The question may be asked, what is the primary valency? What is the secondary valency of this particular compound? What is the central atom? Cobalt is the central atom here. Central metal ion, if they ask, see there is a difference. Central atom, central ion. Atom means cobalt. Central ion means we need to see the ionic pieces. How many? CO 3 plus, central 3 plus. Then primary valency. Oxidation state of the central metal atom is called a primary valency. That is 3 plus. Primary valency 3 plus. Then the secondary valency, if they ask coordination number of atom or molecule surrounded to the central metal atom in a coordination sphere. If you see within the coordination sphere, you will have 6 ammonia. So that's why secondary valency or coordination number for this piece 6. Okay, oxidation state plus 3, coordination number 6. Number of moles of AgCl produced 3. Well, let us go with this example. See here also coordination number 6. What is the difference, sir? Here also 6, there also 6. All 6 are satisfied by the neutral molecule ammonia. Okay, this is the thing. All the 6 coordination number is satisfied by the neutral molecule ammonia. Here also coordination number 6, there is no doubt at all. But in the 6, among the 6, 5 are ammonia, 1 is Cl minus ion. 5 neutral molecule, 1 negative ion is satisfying this coordination number 6. If you take this compound, here also coordination number 6, coordination number 6, okay. So the 6, 4 ammonia neutral molecule, among the 6, 4 neutral molecule ammonia, 2 Cl minus ion. 2 Cl minus ion is satisfying this compound. So this is where you need to analyze the compound. There is that's all about the Werner's postulates. Once again I am repeating the Werner's postulates. It's nothing but every central metal atom have 2 valencies. One is a primary valency, another one is a secondary valency. Primary valency is that is a reason for the oxidation state of the central metal atom. Primary valency is nothing but simply we can say oxidation state of central metal atom is a primary valency. It is a non-directional. It is a non-directional. It is a ionizable one. Okay. It should be outside of the coordination sphere. Okay. It is satisfied by the only negative ions. The primary valency being always positive, in some cases there will be 0. Okay. Always positive, in some cases there will be 0. That's all about the primary valency. Whereas in the secondary valency corresponds to that of the coordination number of that compound. Coordination number of that compound. It is satisfied by the neutral or positive or negative ions. Okay, it is satisfied by the neutral and negative ions. That's all about this. This is the directional. It is the reason for the geometry of the pieces. Secondary valency only reason for the geometry of the pieces. If we compare to this, in each and every compound, all the central metal atoms should satisfy the both valency. Then only it will be a exact compound. Both valency should be satisfied by the whether primary valency or secondary valency, all these two should be satisfied only to give an entire compound. As from this postulates, we are getting to that how the coordination compound is formed. For example, we take a chromium trichloride and ammonia basis. We have discussed there is one inner sphere around the metal ion that is surrounded by the ligand, that is called a secondary valency. Or the second sphere is called ionization sphere or outer sphere. There you are getting that primary valency, the non-directional. These are all we have seen. What is the limitation? Then let us move on to the limitation of the Werner theory. It explains the formation of compound, but it does not explain the color properly and the magnetic property of the compound. Color and magnetic property of the compound is not clearly explained. That is the limitation of Werner theory. What is the limitation of Werner theory? Werner explaining all those how the compounds are formed, what are the primary valency, what are the secondary valency, and so on. But he's failed to explain to how they are expecting color and magnetic property. These are the limitations of the Werner theory. Okay. Then let us have an evaluate question. With this we can conclude. There you have a chromium trichloride hydrate molecule. It giving that it treated with a silver to give a 1 moles of silver fluoride. The question is that the formula will not be given. The chromyl chloride, it is giving the 1 moles of AgCl. What is the formula and primary secondary valency? See, 1 mole of AgCl formed mean 1 Cl should be out. So Cr, I am writing the formula, H2O 4 times and Cl. This will be the formula. Okay. Then what is the central metal atom? Cr3 plus. What is the primary valency? Primary valency plus 3. What is the secondary valency? 4 plus 2, 6. Secondary valency, that is coordination number 6. Okay. 1 Cl should be out. That only when you treat it with the silver ions, you are getting that 1 mole of AgCl. Okay. So likewise they will give in a bad, we can write the formula for this. Okay. Thank you.